Welcome back to CppEurope, just in time for the last session of the day. Do you believe it? We got so far today. Before we move on, I'd like to thank once again Siemens, our main partner. And our next speaker is Eric Niebler. A few years ago, I was writing my book on functional programming in C++, and one thing I was curious was how I could write functional programming but with a nicer syntax, and I found the ranges library, which is really cool. And when I heard that Eric Niebler, who was one of the main leaders on this library, is also interested in another difficult topic, which is asynchrony, I got really excited. So Eric is a long-time member of the ISO C Standardization Committee. His main expertise is modern C library design. He's been busy with multiple Boost libraries, the Range v3 library, but somehow has also found the energy to build abstractions for asynchrony that are fit for standardization at NVIDIA. So I can't wait to see how we can simplify or make easier asynchrony with the right abstractizations. Welcome, Eric. That's all from me, and you have the stage.
Great, thanks a lot. My original plan for this talk was to give exactly the same talk that I gave at CppCon, but I thought, I could do better than that for Europe. I'm going to do something that I've never done before. Today, I'm going to be live coding the sender-receiver abstraction from the ground up from the Executors proposal. But before I do that, I want to make sure that everybody knows where we're going. So I'm going to blitz through some high-level design to give you an idea. So the Executors proposal, we've been talking about it for 10 years on the committee. What exactly is it? So first and foremost, the standard Executors proposal is going to give us a standard asynchronous programming model, by which I mean, it's going to be the recommended way to expose asynchronous computation for the whole C++ community. It is also a way to specify where, how, and when work should happen. It's open and extensible so that you can plug in your own compute resources and have work done there. So some examples might be like an event loop or a thread pool or a system execution context, a GPU, a NUMA domain, or even a cluster. Right. And finally, it's a suite of generic asynchronous algorithms. Algorithms like then for chaining work, when all for launching a bunch of stuff concurrently and waiting for it, and sync wait. So the big ideas in sender-receiver, the three major concepts are sender. And when I say sender, you should think a lazy value. Sender's a lazy value. It's a value not computed until somebody asks for it. So when I say receiver, you should think a continuation or a callback. Or when a sender's done computing its value, it passes the value to the receiver instead of returning it to the caller. And finally, a scheduler. Scheduler is a handle to a compute resource. Might simply hold a pointer to a thread pool, for instance. Okay. We'll show a quick example of what it's going to look like to actually consume this interface. So here is a little bit of code that launches some compute-intensive work, 3 instances of it concurrently on a thread pool, and then waits for it all to finish. We'll look at it in bits and pieces. First thing we do is we declare a third-party execution context, static thread pool from the libunifex library. And then I get a scheduler from it by calling getScheduler. Next, I'm going to create an empty work unit that runs on the thread pool. This work does absolutely nothing, except it does it from on a thread in the thread pool. Now, onto that empty work, I'm going to change some compute-intensive work that will also run on the thread in the thread pool. And we want to do 3 such tasks concurrently. Finally, we want to enqueue the work, wait for it to finish, and return the results. I'll point out that since sender-receiver is a lazy abstraction, until you actually sync wait for the result, no work is actually done. Nothing gets scheduled on the thread pool. No work gets started. If you don't actually ask for the result, then nothing happens. Okay. So that's our complete example of launching some work concurrently on a thread pool. The big idea, the DAO of stood execution, is just simply this: that schedulers produce senders, and async algorithms accept and return senders. The idea is that the system composes itself similar. You just pass senders to other algorithms, and you get back more interesting senders. So I'd like to fill your head with an image of the life cycle of an asynchronous operation. Everything starts with a scheduler, and calling schedule on the scheduler returns you a sender. Now, what happens with senders is that they get connected to receivers. Receiver, remember, is a continuation or a callback. And so you connect the sender and the receiver, and what you get back is an operation state. That's the state that needs to be kept alive for the duration of the asynchronous operation. Still, no work has started yet. It only starts when someone calls start on the operation state. Then it gets enqueued for execution. Time will eventually pass. That operation will complete. And when it completes, it'll notify the receiver that the work is done. Now, everything in this dotted box, these are all implementation details of some algorithm, like maybe the then algorithm. So if you are just a consumer of the algorithms, you just see schedulers and senders. If you are writing generic asynchronous algorithms, you are dealing with receivers and operation states also. When the operation state notifies the receiver, it does it by calling one of 3 functions on the receiver. Either set value if the work completes successfully, set error if it completes with an error, or set stopped if, say for instance, somebody canceled the work before it was able to produce a value or an error. So really, this is the heart and soul of sender-receiver. These concepts: scheduler, which has one function, schedule; sender, which has one function called connect; receiver, which has these 3 functions: set value, set error, and set stopped; and the operation state concept, which has one function, start, which starts the operation. And with that, I would like to get to the business of actually writing sender-receiver code. Well, a lot of that stuff that we just saw is actually not at all hard to implement. And I think by implementing it, it's the best way of recognizing like how the pieces hang together. So let's just dive right into this. The just sender factory, that's something that takes an ordinary value and turns it into a sender that will complete immediately. So let's go ahead and write a just function. We don't know what it's going to return yet. It's going to return a sender, we know that. Okay? So it's going to return a sender, so let's just call it just sender of t. And let's imagine that it's going to store the t. Now we have to write the sender. I've written some keyboard macros to help generate some boilerplate for me. So that's basically the template for a sender. So I might say, okay, this is going to store the value. So let's store the value. Okay. And it has a function called connect, because all senders must implement connect. I take a receiver and returns an operation state. So let's do that. Let's imagine that the just operation stores the value and the receiver. Let's say receiver and self.value. Now I can use my macro to generate some more boilerplate for me. Okay, here's the just operation. And this is going to be parameterized on, let's see, it needs both the receiver and the value type. This is R and AST. Okay, and these just store these as data members. Now, the interesting thing about just is that when you start it, it completes immediately. Okay, so completing immediately means that it just needs to call one of the set functions on the receiver. In this case, it's just going to call set value. So let's call set value on the receiver, which is self.receiver, RAC, and we're going to pass the value, self.value. There. Okay, just like that, we've implemented the just sender. It's all the pieces that we need, and we can see how this works together. I pre-authored a simple receiver that just does nothing but outputs the value and terminates on error or stopped. So we can declare one of these guys as a local variable. We can connect it with the cout receiver, and we can start the operation, and we get 42. So this is the most boring way of an overcomplicated way of computing 42 as you could possibly imagine. But it gets more interesting. The next thing we do is we want to be able to chain work onto other work. So for that, we write a then algorithm. The then algorithm takes a sender and a function. So let's write a function called then. Takes a sender and a function. Class S and class F. And let's imagine it returns a then sender that just curries up its arguments. And it's going to return just an ordinary struct that stores S and F. Okay. Now we have to write then sender. All right. So the then sender is going to return a then operation from its connect function. First, it needs to store the sender and the function. And give it some template parameters. Okay. We're going to need to return this receiver, and we're going to need the function. Let's take a look at what the then operation will look like. on macro. There. Then operation. Now, notice something interesting about the operation. It's immovable. This immovable type is defined up here. It's got a deleted move constructor. So you're only going to be able to construct then operation in place. Still, it's okay to return them because in C++17 we get guaranteed copy elision or guaranteed return value optimization. So things aren't actually moved when you return them from functions. They're just constructed in place under certain circumstances. Okay. All right. So I think we need a receiver. We need a function. All right. Now, what gets stored here? Stored here is, this is actually incorrect. So let's think about this. So we have a sender. We want its result. We want to pass the result of this sender when it's available to this function, f. And then we want the result of f to be passed on to this receiver. So what we want to do here is we want to get the operation state for the then operation, for the inner operation, and start it. So here, up above, created an alias called connect result, which is just getting the result type of calling connect. Okay. We can use that here. We'll need the sender type also. Okay. S, R, and F. Okay. Connect result of the inner sender, and now some kind of a receiver that gives us the behavior that we want. That is, it's going to call the function on the result of S. So that's going to be a then receiver. Okay. And then calling start on the then operation is really just going to call start on the inner operation. Okay. That means over here, we know what we need to do. We need to connect sender, the inner sender, with the then receiver. We haven't written yet. I imagine it's going to take the receiver and the function. So now we have to write a receiver. Yes, I have a macro for that as well. All right. The receiver has set value, set error, and set stopped, as we expected. So let's see, it's going to need a receiver and the function. So let's do that. Okay. Now, I'm going to skip set value for now. Let me go on to set error and set stop. Those are really simple. They're just going to pass the errors through. So let's make sure we call set error on the inner receiver of and the error. Just passing that error through to the inner receiver. And similarly, what we're going to do here is we'll call set stopped on the inner receiver. Okay. Now, set value is where actually the algorithm where it's actually implemented, where the then algorithm is actually implemented. Okay. Oh, let's see, we've got errors here. What's this? Oh, I didn't want this. Okay, good. So what we do here is we want to call set value on the inner receiver. We're not passing the value through directly. We want to transform it with our function. Like that. Now what we've implemented is we have chained some action onto another asynchronous computation. And we can see that that's going to do what we hope. We come down here and we can, let's get rid of this guy and have a look at this one. Well, I can create a sender that takes 42, just 42, and sends it into this lambda and increments it, and then runs the operation and prints it. Now you'll notice like nothing asynchronous is happening yet, but it will. Okay. What's next is the sync wait algorithm. This is a very important algorithm because it's important that we're able to block a thread and wait for the result of an asynchronous operation. You'll probably want to do this in main. So let's see what sync wait does. We know it's going to take a sender. We don't know what it's going to return yet. We know since an asynchronous operation can complete on a separate thread. Yes, is there a question? Okay. Since it can complete on a separate thread, we need to worry about synchronization. So we're going to have a control block. So let's imagine a control block that has like a mutex and a condition variable in it. We'll call it sync wait data. And we're going to have a std mutex. We're going to have a std condition variable. Now, it's also going to store a little bit of extra information. Like if there's an error, we'll want to return that information to the caller. So let's store an exception footer here. And we also want a Boolean to say, to indicate that the work is actually done. And for start at false. It's false. Here we're going to have our sync wait data. That. And now what is it going to return? Sync wait algorithm is going to return, well, however this thing can possibly complete, what value it completes with. But it could also be canceled, so you might not get a value at all. So let's say it returns a std optional of something. And that something is got to be a type derived from S. Really, it's not easy to figure out how a sender is going to complete just by looking at it. There's nothing in the signature of any of these functions that gives you any indication that the sender is actually going to complete by passing an integer to the receiver. So we need to give the senders some meta information. Say using result type equals T. Okay. Now that sender is declared, it's how it completes. And let's also create a template alias for accessing that result type with a nice syntax. Okay. So now we have to do this for all of our senders. The then sender is pretty interesting because you need the input sender's completion type and the function. So let's say using result type equals, and then we can use std invoke, which gives us the invoke result, which gives us the type that a function will return. Invoke result t of f, and then however the inner sender completes, which was the sender result t of s. Like that. All right. So that should get us what we need. So here we should be able to say sync wait result of s. But he gets to see what a bad typist I am. Sync, no, that's not what I wanted. I wanted sender result. Okay. Let's also declare an optional store this type, the value type. Let's create a local alias for that. T equals there, sender result. This is going to be an optional of t. That's going to be the value. At some point down here, we're going to be returning the value. Good. What's next? What's next is we need to connect the sender with something. Well, we need to define a receiver. And the idea of the receiver is that the receiver, when it gets called, when it gets notified that the work is done, it's going to set some data in this control block, and then it's going to signal on the condition variable. And here in sync wait, we're going to be waiting on that condition variable. So let's make a receiver. Oops. Let's make a receiver. That looks a little bit better. So the receiver needs to know about the type that it's going to complete with. So because it's got to store a reference to that optional. It's going to store a reference to the optional. And it's also going to store a reference to that control block. Data. Oops. This one's called data. Let's call that one data. Let's call this one value. Okay. Now things get interesting. Now I need to worry about mutual exclusion. So let's declare a unique lock. That grabs the mutex. Right. Good. We've grabbed the mutex. Now I can store the value because I've completed successfully. I'm in set value. I could store the value in the optional. So I could say self dot value dot in place of value. Okay. Let's signal that the work is done by setting that flag, self.data.done equals true. And now we signal on the condition variable, self.data.cv dot notify one. Okay, that's our set value. And the others are going to be very similar. Obviously, in set error, we're not setting the value. We're setting the error. Data error equals error. Okay. And in set stopped, we're not doing that at all. We're just signaling that the work is done. All of these functions as their last step, they notify on the condition variable. Okay. Well, let's connect the input sender to one of these receivers. I called it sync wait receiver. Takes T, and it's going to take the data and the value as references. And I start operation. Okay. Now I need to wait on the condition variable. Eventually that work's going to complete, and the receiver's going to notify me that the work is done. So I need to say data.cv, CV dot wait. Oh, right. The first parameter to wait is actually a lock. So the first thing I have to do is take the lock. Lock. And as Rainier was saying, when you wait on a condition variable, it's best to pass a function to tell you whether or not the work is actually done, so you don't get spurious wake-ups interfering with your function. So what we want to do is we want to return data.done. I need to store a reference to the control block. Okay. But when I get past here, I know the work is done. So I have to check to see how the work completed. It could have completed with an error. Did we just rethrow the error? Okay. Otherwise, we just return the optional. Okay. That should be correct, I hope. I should be able to create a sender and sync wait on its result and get back a value and print the value out. Yep. Works as expected. Thank goodness. And you'll notice now that, just like I promised, if you're just consuming the interfaces, you don't have to muck around with operation states or receivers, right? The user of just and then and sync wait, they can be blissfully unaware that there's receivers and operation states being created under the covers. Still, nothing asynchronous has happened yet. And it's time we do something about that. So we're going to create a run loop execution context. And kind of think of this as a first in, first out, multi-producer, single consumer work queue. So you can imagine this implementation is going to get a little fun. Okay, let's get started. have a run loop. This thing's also going to be immovable, by the way. Okay. Now, what we're going to be doing, we could, of course, store all of our work items in a vector. But that requires dynamic allocation. And sender-receiver is designed so that you can take advantage of the structure of the computation to avoid dynamic allocations entirely. So what we'll be doing is building an intrusive linked list of work items. So if it's an intrusive linked list, we need list nodes. So let's go ahead and make ourselves a list node. Or the task. This one's also immovable. And it's going to have a pointer to the next task. And it's going to have an execute function. Now, I'm going to do something a little clever here. This is going to be a circularly linked list because it makes the code a little bit simpler. I'm going to do something, maybe you've never seen this before. I'm going to initialize the next pointer with the this pointer using member initialization. Okay, now if I declare a task, I've essentially declared a circularly linked list that just points back to itself. Okay. Now I need to create an operation state that's going to implement this interface. Let's call this thing operation. Wrong thing again. Something's wrong with my macros. Okay. Let's say we're just calling it operation. It's going to be parameterized on a receiver. Why is it going to be implemented, parameterized on a receiver? Well, this is going to be an execution resource that's going to be coughing up a scheduler. The scheduler has a schedule function that returns a sender. So we're going to be implementing all of that. Well, what do you do with senders is you connect them to receivers. The receiver that you connect to that thing then is going to be the item of work. So the receiver is the item of work, and this is a queue of work items. So here is our work, the receiver. Okay. Now, what is start going to do? Start's going to insert this operation into the queue. So let's say we're going to also have to store here a reference to a run loop, back to the run loop. Operation, where's the reference to the loop? Okay. And what we're going to do here is we're going to push this thing at the end of the list. Let's imagine that there's a function called pushback on the run loop. There isn't one yet, but we're going to write one. We also need to implement the execute function. And it's an override. Final too. So we could say override and final. But we're going to set the value on the receiver. Now, we're trying to make our lives a little bit simpler because this is not full-fat sender-receiver. This is a simplified sender-receiver. And so let's imagine in this implementation of sender-receiver, everything completes with exactly one value. Oops. It's complaining about that because I'm not inheriting from task. All right. So let's imagine that there's some none type that represents not a value. Now we need a none type then. Let's say there's a none type that's just empty. All right, now what else do we need? We probably need a constructor for this thing. Initialization is going to get a little hairy. So let's declare instruction, take the receiver, and it's going to take the run loop, the reference. Okay. Say receiver, ignore shadowing warnings. This is legal code. Okay. So far, so good. We have the bits and pieces that are going to make up our list. So now let's declare some data in our run loop. Our run loop is going to be storing the list. You know, it's going to be storing at least the head of the list, right? So needs the head. So we can declare a task, call it the head. Store it by value. This is not a pure virtual interface. So I can store it by value. And what it's storing here is a pointer. It's got a next pointer that's pointing to itself. So here, head is pointing to itself. It is now a circularly linked list that is self-referential. Oops. Since we're going to be pushing to the end of the list, we also want to be able to get there quickly. So let's store a tail of the list. And to start off with, it's going to just point to the head. Now this is going to be, it needs to be thread safe. So let's have a mutex and a condition variable. Like that. Now we need to implement that pushback function that we're calling here. Returns void. It's going to take a pointer to a task. And it's going to add something to the list, the back of the list. Right? So we have to manipulate that linked list. First, we need to grab the mutex, of course. Okay. Now, since this is going to be the new end of the list, and because our list is going to be circular, we know that its next pointer has to point back to the head. Let's do that. Right? Now we need to fix up what is the current end of the tail, which is currently pointing back to the head as well. We don't want that. We want it pointing to this operation. So we could say tail, tail's next should point to this operation. Now we have a new tail. The tail is also going to be this operation, last element in the list. So we could say op equals, oh, tail equals. Oof. All right. And then we have successfully inserted the element into the back of the list. And now we can notify on the condition variable that there's work to be done. Now, since we have pushback, you can imagine we're also going to need pop front for dequeuing work items so that it can be executed. So let's write that one too while we're at it. You'll notice I'm not worrying about exceptions or const or private or public or even constraining template parameters with concepts. I would do all that in a real implementation, but let's just keep it simple for now. So again, we're going to be grabbing block as the first thing. Now what we want to do is we want to wait until someone notifies us that there's work to do. So we can wait on the condition variable. Again, passing a lambda. Tell us when we're really done. This parameter, and we want to, what do we want to do? We want to only say that we've stopped waiting on the condition variable when there is an element of work to do in the list. And that happens when the head is not pointing to itself. So let's do return head.next is not equal to the address of head. Okay. Now we know we have work in the queue, so what we want to do is pop it off the front. So we want to return front, that is head.next is the first element in the list. But we also want to update head.next because we're popping this thing off of the list. So what we can do is we can use the std_exchange function. It's a very handy function. I use it all the time. Half of a swap. Going to return you the value of this, but it's going to update it also. So what it's going to do is it's going to take this value, stuff it into here, but what was in here before we changed it is actually the return value of std_exchange. There. And that's our pop front function. All right, so enough with the setup. Let's imagine we need to get a scheduler. So let's say scheduler get scheduler. Earn. We need to refer to this run loop. Don't have a scheduler yet, so let's write one. And schedulers, let's see. First, it's going to store the run loop. Okay. But it implements the schedule function to return a sender. So let's write that. Friend. It returns a sender, and it's called schedule. It takes the scheduler. It's just going to return sender, which we're imagining is just going to store a pointer to the loop. Okay. Typos. Okay. Sender. We definitely need a sender too, right? Right. Here's our boilerplate for the sender. All right. We know this connect is going to return one of these operations, parameterized on the receiver type only. This is actually not going to be a template. It is going to store pointer to the run loop. Now, constructing one of these operations, we wrote a constructor. It takes the receiver, and it's going to take a reference to the run loop. So that's self.loop. That. All right. Now it's a run loop, so it needs a run method. A run method that's going to EQ all the elements and execute them in turn. It's pretty simple. We've already done all the hard parts. I'm just going to be popping stuff off the list. And then executing them. The whole run loop. Now, there's a problem here. The problem is that we've given ourselves no way to ask the loop to stop, to let it know that, okay, I'm not going to add any more work to the queue, and I want you to finish now. This run loop is going to run forever. So we need to do something different. So let's imagine there's a finish function. And it's going to be updating a data member just to signal, okay, I'm finishing. So let's say it's called finishing equals true. Means that I need a Boolean here. Finishing is initially false. But that means that in pop front, we have another exit condition from this wait on the condition variable. So it's either if there's an element in the list, or you're finishing. And here now we have to check, do we have something in the list before we continue? Head.next is equal to head. Then we know the only reason we broke out of this condition variable wait is because we're finishing. There's nothing in the work queue, and we're finishing, so just return no. All right. But since we're accessing this data possibly on another thread, we are definitely going to need to acquire the lock before we do anything here. And we'll need to notify on the condition variable that the state has changed. All right. Oof. There. Hope I got that right. That is our run loop. What we should be able to do now is declare a run loop, get its scheduler, create an operation by connecting it with the receiver, and then starting that operation. Well, let's see. Oh. No type name result in run loop sender. That's right, we didn't declare how that sender completes. So here's our sender, and it's going to be sending that none type through the value channel. So let's say using result t equals none. Okay. So notice I've started the operation. I didn't get any output. All right, that element is now sitting in the queue. I could do this as many times as I want, queue up a whole bunch of work. Now I can tell the run loop, hey, I'm done adding new elements to the queue. And go ahead and execute that loop. And there. Now I get those two work items executed and the output I expect. But unfortunately, we're back to mucking about with receivers and connect again. We don't want that. Let's wrap the run loop up in something that drives the run loop on a separate thread. Let's do a thread context. And I'm going to cheat a little bit. It's implemented in terms of the run loop. And it's going to have a thread. And its thread function is really very simple. All it's going to be doing is calling run. Now, it needs a scheduler, but it can just use run loop scheduler. So we could say using run loop get scheduler. We also want a way to finish the work, so let's do the same thing here. For the finish function, let's bring that into scope also. Now, the last thing we need to do is that thread needs to be joined. So we can give ourselves a join method. Now we've implemented our thread context. This is an execution context that wraps up a worker thread, lets you schedule work onto it. All right. Now what we can do is we can schedule some work onto that worker thread, chain some other work onto that, and then sync wait for the whole thing to finish. What did I do now? Oh, that's right. Schedule is completing with a none type, not an integer. So let's Let's make that a generic lambda. All right. Oops. I hope that did, whoops, hope that did the right thing, and we should be able to get the correct value out. Oh, I wanted val 7. Okay. Ah, 43. Right, that's 42 plus 1, 43. And now I have work doing on a work on a separate thread. And I can add as many work items to this thread context as I care to. All right. So that's the whole thing, soup to nuts, sender receiver, start to finish, including just and the then algorithm and the sync wait algorithm and run loop and thread context, execution contexts. So I hope that this puts to lie the rumors that I've heard that sender receiver is very complicated. I can code up a toy sender receiver. It's a toy, I admit, but in under an hour. So, all right. That is all I have for you guys. This was super fun, and thanks for joining me for this. All right.
All right. Thank you, Eric. We are still waiting for some questions. I guess people were very interested in what you had to show as an example. So it looks simple for you, but I'm not sure if it's so simple for... I guess you've done this multiple times, right? For your...
This is actually the very first time I've ever live coded during a talk.
Oh, cool.
Yeah, I want to try something different.
Anyway, so Christian says that this was fun.
Oh, good.
And thank you very much. All right. So we are waiting for some questions, and it doesn't have to be about the talk. It can be about other things as well.
Yeah.
As I said, I really enjoyed the ranges library. Perhaps if I can ask a question first until people start. What is the history of the ranges library? How did you start with that?
Oh, the history of the ranges library, it goes way back. It starts with boost range, which is not authored by me. I believe it was written by Torsten Ottosen. I hope I'm getting that right. But this was like back around 2000. There was a range library, and all it included was some free functions, begin and end free functions, and some algorithms that just took ranges and forwarded to the standard algorithms. And that was the extent of the range library in Boost at the time. And I remember thinking, well, we could do better than this, because ranges give you the power to compose. I can write range adapters that and build pipelines out of them. And I kind of got this idea from another Boost library called Boost Iterator, and it had iterator wrappers for things like a transform iterator or a filter iterator, which I thought was brilliant. And I thought somebody really needed to put Boost Iterator and Boost Range together. And so I created a little toy library, proof of concept, and I shopped it around on Boost. And there was a lot of interest. But I never really felt like the ideas were polished. So I never took it the rest of the way because I hadn't worked out all of the design issues. But that didn't stop Torsten, who really liked the idea of having range adapters that you could pipe. And so he included it in what he called boost range v2. So that was the history there of the range adapters, and that really took off. And then I realized, late in the game that concepts were really going to be a thing. It was actually really going to happen. I thought it was going to happen in C++17. It almost did. And I also realized that we're going to need a whole new version of VSTL to take advantage of concepts. They're remarkably difficult to reverse engineer into an existing code base. It's kind of nicest to have a clean slate. So I thought, there's going to be a heck of an opportunity when we standardize concepts. We'll have a clean slate to work with. So I started writing my range v3 library, which I called range v3 because I thought it was going to be the third version of boost range. But C++17 was coming up hard and fast, and I didn't think there was going to be enough time to get it into boost first. So I just went straight to GitHub and then wrote a proposal about it. And that became the ranges TS, and which ultimately became, in C++20, stood ranges. So that's the history there. I mean, that's an abbreviated history. It took, I think, 5 years start to finish.
Yeah, that's one thing that I was thinking, that it probably took some time. And another question, there are a couple of questions now, but I have another one. What did you find more difficult or most difficult when designing a library, like ranges or asynchrony or something like that?
The hardest part about designing a library is deciding what it is that you're building. Because it's easy to think you understand a domain and what a solution would look like. But oftentimes you really have no clue. Best you could do is come up with a prototype, play around with it, figure out okay, how am I going to use it? How are other people going to use it? And then, did I build the right thing? There have been times when I've built a library and then realized that was actually not the right problem to solve at all. Throw the whole thing out and start over again. And I've done this 3 or 4 times on some projects before I really feel like I understand what the domain is well enough to find the right abstractions for it. Yeah, right. That's and there's no shortcut there. It's just a long, hard slog. Yeah.
Yeah, and I think it's an incremental process as well. So you try and you try again, and then you figure out some more what you're trying to solve, and sometimes it's a dead end and so on. All right, so there are 3 questions right now, but I would encourage people to post some more. Most voted question by Remy. Thank you, Remy. What would you change in the standard if you could at will to make asynchronicity even easier?
What would I change in the standard to make asynchrony easier? Well, I mean, I would love a time machine so we could go back in time and add the sender-receiver abstraction right from the get-go in C++11 when we got threads. The problem is, we went to all of this hard work getting language support, core support for threads, and doing the memory model and doing, you know, atomics and all of that stuff. It was an enormous lift. And then at the very last minute, we were like, oh, we should probably expose some of this stuff in the standard library. So, like, here's some stuff. There's a thread. Here's a mutex. You know, here's a future. Here's std async. I mean, all of it is deeply problematic, right? Future, the std future is almost completely useless because you can't chain more work on it. All you can do is block. A std async is useless because you almost never want to just launch some work in a new thread, and get back a future, which then you can't chain work onto. Again, you have to block. And then, you know, the primitives we're giving people are mutexes and condition variables and locks and things like that. But as you know, as most people who have done asynchronous programming know, threading with you know, explicitly taking locks on mutexes, it doesn't scale, right? That doesn't compose. You end up with deadlocks, and you end up with memory leaks, or you end up with shared putters everywhere. And so, yeah, if I could go back in time, I would start with something like sender receiver or even coroutines, because that represents structured concurrency, as opposed to that sort of ad hoc, you know, spin up a thread and wait on a mutex sort of unstructured concurrency, which is just really difficult for people to reason about. Yeah, but like coroutines are a huge step forward, because it lets you write structured code, and it looks pretty much like your ordinary like synchronous functions. You just sprinkle co-await here and there, and then things just work. It's really nice.
All right. The next question from Adrian. Can you share a link to your code?
Sure. How shall I get that to people?
Well, if you push to GitHub or someplace, you can then send a link, and we'll add it into the materials that we publish afterwards. I think that's easiest.
Sure thing.
I'll
do that.
Yeah, or if you have a link now, you can send it on Google Meet, and then we'll figure it out.
I don't have a link. I could probably get this code into a Godbolt and send around a Godbolt link. Here.
Yeah, or something like that. Yeah.
Let's do that. Here, Godbolt. Org. And okay. Yes. And compiler options. This needs C++ 7.20 equals C++ 20, and it needs to link to pthread. Okay, I think that's it. So let's grab a short link for that, and then shall I post it into the what's it called?
Google Meet
Mosaic Works. Yeah, there. Yeah. There, I just posted a Godbolt link in the chat for the for CppEurope. Yeah.
Okay. Okay. You already posted in Crowdcast. Perfect.
In Crowdcast, yeah. So that's where you could find it.
Yeah. Awesome. Okay. Next question from Xavier. What features from Ranges v3 do you miss the most in the STD Ranges implementation?
Oh boy. I miss the most. I mean, there's so many adapters that belong in the standard that just aren't there yet. So I miss things like repeat or Cartesian product or gosh, there's so many. Concat, you know, we don't even have concat. I think we just have join. A lot of these are either coming in C++ 23, like they've already made it. I know Cartesian product and repeat are coming. I forget what else, but there's others. And then there's a whole bunch of people, not me, who's driving it forward now, which is really exciting to see. And it's good because you know, I'm pretty focused on async these days. So there's a little group of committee members who've picked up the ranges banner and are running with it. So yeah, there's a whole roadmap of features that are coming in future versions of the standard, and most of them are lifted from range v3.
All right. Well, there are no more questions. So I'd like to thank you so much for this live code. Hey, actually, another question. Is there a pattern that can contain the sender-receiver over the RPC model, especially when it's a P2P network?
Sure, yeah. You can easily abstract an interface, a network interface like that behind a sender. Yeah, any async computation that gives you a way of specifying a continuation, yeah, you can turn it into a sender without too much hassle, right? And then if you do make your asynchronous APIs return senders, then you'll be able to pass them to the standard generic asynchronous algorithms of the future, of which, you know, we're hoping to have a whole bunch. You know, not just the ones that I showed, but like a whole raft of them, including time-based ones like timeout, some windowing stuff, some reactive stream stuff. Yeah, I mean, there's a lot of exciting stuff that we could do from here.
So actually this also sets the base for something like reactive programming in C++?
Yeah, for sure, yeah. You can kind of think of a range of senders as a reactive stream, like a really simple one, right? So you write a range for loop, and right in the executors proposal, senders are co-awatable. So you can, you know, in a loop process your reactive stream and co-await on the arrival of each element.
Right. That sounds very, very cool. Okay. So we only have 1 minute left. Let's see if there's another question coming, but for now, no new questions. Anyway, I think it was a great talk and a great live coding session. I love seeing people doing live coding at conferences, and this was also on quite a complex topic.
I was nervous, never having done it before.
Yeah, I know how it is. We used to say that we need to pray to the live coding gods for things to work, because you never know what doesn't work.
Yeah.
All right.
I had installed a local instance of Godbolt, or a compiler explorer, just to you know remove one extra variable from it.
All right. So thank you so much. This is all the time that we had. Xavier, Liviu, Remy, Mika, they are telling you great talk. So we got very good feedback as well. I will move to close now. I have a few short slides to show. So just a moment to quickly switch to my screen. So as I said,